The last type of intermolecular forces that we will consider are called dispersion forces. These are the weakest because they do not consist of permanent charges. So consider a molecule like carbon dioxide. Now, these have bond dipoles in carbon dioxide. This oxygen is partially negative, so is this one, and the carbon is partially positive. However, we have bond dipoles, one pointing one direction, the other pointing the other direction with the exact same magnitude, and therefore they cancel each other vectorially, and so there is no dipole moment because the bond dipoles cancel when we draw them as vectors. However, electrons move, and they move very rapidly, and they move a lot faster than the nuclei in atoms and molecules. So what can happen is, consider at an instant where we have a carbon dioxide molecule, and I'll draw this just kind of oval around it to depict where the electrons are. And I've drawn the oval so that it's bigger on the right side than the left side. So that just means that there are more electrons on the right side than on the left. So what this will cause is a instantaneous dipole. Because there are more electrons in this region of the molecule on the right side than on the left side of the molecule. And in an instant, though, that will collapse, and we could have something that looks like this, where now we have more electrons on the left side of the molecule than the right side, and so we'll have partially negative charge on the left, partially positive charge on the right. This is again another instantaneous dipole. So at any instant there could be a dipole moment in carbon dioxide, but over on a time-weighted average there is no dipole. All of these instantaneous dipoles on average cancel out. So say if I have two carbon dioxide molecules and one of them has an instantaneous dipole so that there is more electron density on the right side of the molecule than the left, so it'd have a partially negative charge on the right, partially positive on the left, and say there's a neighboring carbon dioxide. Well, this can induce a dipole moment in this other carbon dioxide. Since this part is negative, it's going to push electrons away from it, this side. And so what will happen is it will form an instantaneous dipole in the carbon dioxide next to it, so that we have a partially negative side on the left with a lot of electron density and a partially positive side on the right with a little bit of density. And this is called an instantaneous dipole induced dipole interaction. So we have an instantaneous dipole in carbon number 1 here, which induces an instantaneous dipole in carbon dioxide number 2. So there is an instantaneous attraction between them. Well, since these dipoles are only instantaneous, they're going to decay, and therefore the attraction will decay along with it. So these attractions only happen for an instant, and then they're gone. So that's why they're called induced dipole and instantaneous. So these interactions are very weak compared to the others. Now, as another example, say I have a molecule that does have a permanent dipole. Say I have the HF molecule again. So it has a permanent dipole moment, permanent charge separation. What if I have hydrogen near it? Hydrogen H2 does not have a dipole moment, but this dipole in HF can induce a dipole in H2. So it can push electrons in H2 so that this end becomes partially positive to interact here, and this end becomes partially negative, supposed to be a negative, to interact here with this hydrogen. So this is called a dipole induced dipole interaction, because this has a permanent dipole and it induces a dipole in a molecule next to it. Now this will be a permanent attraction because we have a permanent dipole, and it can induce a permanent dipole into the molecule next to it. So this is different from the instantaneous dipole, which collapses and is changing all the time. This one's permanent because of the permanent dipole of one of the interacting molecules. Now, how can we estimate or guesstimate the relative strength of these dispersion forces? Well, they have to do with the relative strengths of the instantaneous dipoles. So as the electron cloud around a molecule is more easily distorted, you can have a larger instantaneous dipole. So electron clouds that are very large are easily distorted. Electron clouds that are smaller are harder to distort. So the larger the molecule in general, Q, the larger dispersion forces are present.